All right. Hi, everybody. Thanks for joining us again today. It's Wednesday, June 10th, 2015, and we're going to go through and talk here for a little bit about I think this is now the fifth or the sixth webinar in the series. Sorry, I think I'm actually losing track. But we're going to talk about equilibration and enclosures today and spend a little bit of time actually not on a whole lot of data, although I promise we will have some good graphs to go through and look at here in just a little bit. So again, thanks for joining us. My name is Jeremy Linden. I'm the Senior Preservation Environment Specialist at IPI. And I'm joined in the room today by my colleague, Chris Cameron. He's going to be running some of the technical stuff in the background, and he'll be listening and answering any questions that come in and just kind of running the show in terms of managing the webinar for us today. And in addition, as with times past, if you have any problems with technical support or you need any information on how to join the webinar, our colleague Lauren Parrish is available here at IPI. Her email and her phone number are listed here. If you have any problems, do please feel free to get in touch with Lauren, and she'll do the best that she can to get everything straightened out and make sure you can tune in and join us here for the next hour and a half or so. As with before, any questions that you have during the course of the webinar, please feel free to use the question box to send those in. I won't see them directly. Those actually get filtered through Chris, and he will answer what he can during the course of the webinar, but anything else, we'll try to save some time here at the end of the program to get to some of those questions, and we'll try to get to as many as we possibly can before we need to wrap up for the day. And this is, just so you know, this is presented with support from the National Endowment for the Humanities through an education and training grant. This is actually the third time that we've given this series of workshops and webinars. We started this out last year in 2014 with a series of two-day on-site seminars and on-site workshops. And here in 2015, we started back in February, and we're moving up through and giving one webinar per month, and going to continue that schedule in the program on up through October. So hopefully you'll be able to join us for the majority of these. For those of you who have joined in the past or have listened in the past, thanks for continuing to be with us, and we're going to have a good time for the rest of the series. The overall program, the goal is really to develop a better understanding of how we can balance the needs of both collections and energy consumption within our buildings. The key here is how do we achieve preservation sustainably? And along those lines, it's hopefully not just background information, but our real intent and our goal here is to be able to provide some practical guidelines for how to manage and reduce risk to collections that might result from different energy practices that we might try or experiment or think about. Up to this point in the series, we've talked an awful lot about preservation and about the impact of environments on collections, and talked a little bit about temperature and relative humidity and dew point and relationships on along the way. And from here on out, after we finish this particular topic today with enclosures and equilibration, we're going to really start moving into some of the more mechanical aspects of this and talk a little bit about buildings and operation, mechanical systems, and how those relate to creating the preservation environment that we exist within and that we're trying to take care of the collections within. So just a heads up as to what's coming in the future. Today's focus, we're going to go through and just give a couple of base definitions, try to get everyone speaking the same language or on the same page if we're not already. We're going to work through some of the basics of thermal and moisture equilibration and how that works in a physics sense, if you will. Some basics of equilibration behavior. And then we're going to address specifically dryness and dampness. And I know we've done this a little bit in the past, just in terms of looking at materials degradation. But I do want to approach it again and maybe a little bit of review today, just thinking about it in the context of this equilibration and how rapidly it is that materials feel what we interpret as these feelings of dryness and dampness in different environments. And we'll go through just briefly, again, the risk to collections materials of each of those, but the bulk of today is really going to be spent on some of the research that we've performed here at IPI over the last 20 years or so that looks at rates of equilibration for temperature and relative humidity and looking at collections materials. And not only looking at how quickly collections materials may equilibrate to different conditions, but what the impact of different types of common enclosures and common housings have on that rate of equilibration. So we're going to provide some data that we have. It's by no means all-encompassing. A lot of this is just meant to give us a better understanding and a better perspective, if you will, on how this process works. There's a lot more research to be done in this area. We'll talk very briefly in terms of what that might look like. But I hope you'll take today as an introduction to this overall topic and just a good opportunity to kind of think a little bit more about how this actually works in real life. So, to step in to begin with, a few definitions. Let's just talk equilibrium here. I think everybody should be fairly familiar with this term, or at least with the idea, if you think about the scales of justice or whatever it is that equilibrium means to you. But in this particular case, we're just going to take a very standard definition of a balance between opposing forces or actions that can be static or dynamic. And what we recognize is that in our everyday environment and the environments that we're creating to preserve collections materials over time, that this is oftentimes a very dynamic relationship. We've talked in past webinars about how interior collections environments, for all that we in the past have tried to hold very steady state flat line temperatures and relative humidities. And for all that much of the thinking is changing for different types of materials, recognizing that in particular wider ranges of relative humidity may be acceptable, largely appropriate for different types of collections materials. We find that equilibrium between the material and the environment that it sits within is a constantly moving target, if you will. It doesn't sit in stasis. Not everything is exactly the same all the time. And we understand and recognize that as the environment around an object changes, the object is going to begin to change in response to that environment. And what we know is that equilibrium is reached when the material is fully equilibrated to the amount of heat or moisture in the surrounding environment. And hopefully the graphic over on the right will help with that idea a little bit. And the second concept that we just want to cover real quick is this idea of hygroscopy. And again, this is just looking at it in a very base manner, is the ability of a substance to attract and hold water molecules from the surrounding environment. So we're talking about materials that can, by and large, absorb moisture. It's just a very simple way of thinking about it for everyday practicality. But the key is that any material that is hygroscopic is going to experience equilibration as the amount of moisture in the environment surrounding it changes. So hygroscopic materials will either take on or give off some moisture based on whether or not the surrounding RH, and the relative humidity here is the key, but based on whether or not the surrounding RH goes up or down in relationship to the amount of moisture contained in the specific object. That object will either give up some of its moisture to the surrounding environment, or it may take some of it on if the environment has more moisture than what the object is currently holding. So if we move in and just start to think about these ideas of equilibration, and we'll get back to that hygroscopy concept in a couple of minutes, but just looking at the idea of thermal equilibration, and what is it that we're talking about? Thermal equilibration is essentially the process of adjusting to the ambient temperature of the environment. And what we recognize and what we know is that materials make the adjustment from the periphery or from the outside surface area of the material. And the core of that object is going to respond more slowly. Eventually, it will also come into equilibration with the surrounding temperature. What we recognize is that objects have to be within a particular temperature for a long enough period of time in order for their core to reach that full equilibration. Now, thermal equilibration is something that, when we think about what that rate of change is or how quickly it may occur, what we've found in experimentation, and what a lot of other researchers have found, is that most materials will adjust to the temperature of a new environment really within a matter of hours. So as we start moving forward, or as we get into the further webinars and we start talking about different strategies or different concepts in terms of managing an environmental control, what we recognize is that adjusting temperature within a particular preservation environment is something that the collection is going to feel relatively quickly. In many cases, what we're working with, or the majority of what we've looked at, which is films and book and paper, a lot of that media is going to come to full equilibration of a one-time temperature change inside about 8 to 12 hours, give or take. So in many cases, it's not even a matter of a full day's worth of time before an object is going to feel the full temperature change at the core, at its core. Now, that being said, the time that the object needs to adjust to that temperature change, that one-time temperature change, is influenced primarily by the amount of the exposed surface area of the object and the thermal mass of the objects in total. What we do realize is that the greater the exposed surface area, the faster the temperature equilibration of the object is going to be. And that being said, the greater the thermal mass, the more density we have of the object, the more time it's going to take to fully equilibrate as a whole. And we'll get to this a little bit further when we start talking about different manners and types of storage, and where it really comes into play and what this has really brought to light an awful lot is how it is that large bookstores or areas where there's a large density of collection material that provides both a great thermal mass and also in many cases reduced surface area, what the impact of that particular arrangement can be on rates of equilibration. Now, the thermal equilibration studies that we've completed and that other institutions have studied do show that when it comes right down to it, it's the temperature level and not the temperature fluctuation that is most likely to cause damage in collections. And when we look at temperature and equilibration, think back to the different types of decay that we've talked about previously, and most of this that we're concerned about is going to be rates of chemical decay. And what we know at the end of the day when we look at accelerated aging, when we look at the impact of temperature on the rates of chemical decay, it's that very simply put, the higher the temperature, the faster the chemical reaction, and the lower the temperature, the slower that chemical reaction for organic materials. And as we look at that, we realize that it's not the rate of fluctuation or how often the fluctuation occurs, but the actual level of temperature, the actual temperature condition that an object is feeling that is what essentially drives the rate of that reaction. Now, in this case, or where the concern really comes into play, is that if we have sustained high temperatures in a given environment, this is going to have that greatest significant impact on the stability of the collection material overall. And the key is managing, and we've talked about this in the past, but being able to manage those high temperature extremes and try to reduce what those conditions are that the collection feels over time. The downside is we also realize that as the environments reach those temperature extremes, the collection now will feel those relatively quickly. To go in and think about moisture equilibration for a couple of minutes, that's just simply the process of adjusting to the ambient relative humidity of the air by an object that can absorb or desorb moisture. And again, we're getting back into these hygroscopic materials. So if you will, there's our good example of bread and how quickly it can either become stale or take on moisture and soften back up based on the amount of moisture that surrounds it. Now, studies have shown most materials adjust to changes in relative humidity in a matter of days or weeks, and notice that this is significantly slower than the rate of temperature equilibration. And in this case, we've got a few more variables going on than we do with typical rates with what it is that determines the rate of thermal equilibration. And in this case, we really do have to think about what is that hygroscopic nature of the material, how easily will it absorb and desorb moisture from the surrounding environment. Getting back to the idea of surface area, what are its dimensional characteristics and what is the amount of surface exposure through which the moisture can enter the object? And finally, as we'll see in a couple of minutes as we start getting into some of the graphs, the surrounding temperature also does influence the rate of moisture equilibration and can actually have some pretty startling and in many cases surprising results for us as we start to look at what this rate of moisture equilibration is, especially in enclosed environments. Now, thinking about the actual process, as relative humidity increases, we know that hygroscopic materials are going to absorb moisture from the surrounding environment. Makes perfect sense. But as relative humidity decreases, we also know that those same materials are going to give up some of their moisture to the surrounding environment. So we have this constant state of fluctuation back and forth, if you will. If we have an environment that varies between relative humidity conditions, whether on a daily basis or more particularly, as we'll show in just a couple of minutes, on a seasonal basis, where we might have various seasons or various times of the year where different areas have high relative humidity conditions, followed by periods of the year where there are more dry conditions or lower relative humidities. What we'll find, though, is that over time, that total moisture equilibration is reached when the moisture content of the material, when the actual moisture contained in the material, is found to be in balance with the relative humidity condition of the surrounding air. And this is a slightly, I'm going to just put it out there, that it's a little bit complicated in terms of concept, and it's difficult to illustrate. What you'll see as we get into the graphs is what we're actually illustrating is the comparison of relative humidity in the ambient condition, or the air surrounding an object, with the relative humidity at the core of the object. We're actually looking at the relative humidity of the air held in the center of an object in a hollowed out space. And the reason for this is that it's in many ways, from an experimental design from our perspective, one of the easiest ways to see what that rate of moisture equilibration is, even though we're not as per the loggers themselves, measuring what the actual moisture content of the material is. We're using that interior RH in that small air pocket as a representative to be able to compare what is going on between the core of the material and the exterior of the material. So what we find, what's really significant at the end of the day, it's that the wide and sustained fluctuations in RH, in other words, those large seasonal fluctuations and variations that we see, are what increase that rate of mechanical decay. It's the fact that over these long periods of time, collections can come into full equilibration with these extremes in relative humidity. Because we know that for many materials, especially in ways that we typically store them, for many materials, RH equilibration is a fairly slow process. And as we said before, it may take days or weeks or oftentimes even months, depending on what your housing arrangement is. It's not necessarily those daily short fluctuations in relative humidity, even as much as 10 or 15%, that most objects are going to feel. Instead, what it is that drives the vast majority of the mechanical decay that we're concerned about, at least in book and paper and film collections, what it is that is really driving this are these long, prolonged periods of relative humidity at the extreme conditions, either very dry or very damp, when the material has the full opportunity to equilibrate to that extreme condition. So the goal here is really to avoid those prolonged periods, right? The longer we're at a dry period, the more risk we have for mechanical damage moving forward, and the higher RH that the material can equilibrate to over time, then not only do we have the increased risk of mechanical damage, but we also have increased problems with rates and possibility of mold growth. So dryness, what are we working with? What are we thinking about? Now, we've talked about this a couple times over, so we won't spend a whole lot of time on it. But the reality is that dryness comes in a lot of different shapes and sizes, right? Typically, when we think about dry, we're talking about low relative humidity conditions. And that's how we're really kind of, if you will, that's the perspective that we have on this condition. We're not necessarily looking at low total moisture content, but we're thinking about low RHs to the exterior environment that are going to drive the moisture content of the objects that live within them to a very low level, to a low equilibrium moisture content total for the object. This happens in a number of different ways. We have winter dry conditions in northern and northeastern U.S., throughout Canada, as well as throughout portions of Europe and northern climes around the world. But also around the world, we have a number of different arid climates that may either be dry year-round, if you will, with very low moisture contents and very low relative humidities, or they may just have a prolonged period of dryness throughout the course of a year that is maybe interspersed or interrupted for a short period by a wet season that doesn't last nearly as long. And we're looking at it again with those 2 points. We're concerned from both the lack of moisture in the environment in terms of the absolute humidity, or what is the lowest dew point condition throughout a particular environment, but also what is the low relative humidity that occurs. In other words, what's the relative humidity of the space when you take into account both the absolute humidity and dew point, as well as the temperature of the environment that you're living within. Just as a very brief overview real quick, and just reminding us to go back to what we were talking about during the last session, that dew point temperature is a representation of the actual moisture content of air. In other words, we use it to think about absolute humidity, even though they're not one and the same. And what we know is that if we have a high dew point condition, if we have a dew point condition where we're talking about 60 degrees Fahrenheit, even higher on up to 20 degrees Celsius, 70 and 75 degrees Fahrenheit, there is a lot of moisture present in those conditions. And when we look at tropical or when we look at high moisture environments where dew points may be even higher, then we know we have a lot of moisture and water to contend with in terms of creating the appropriate preservation condition. On the flip side, if we're looking at it and we have a low dew point condition in these arid or drier climates, whether it's seasonal or whether it's a year-round condition, we also know that there's less moisture present. And on that side of the scale, we're going to be more concerned about dry conditions and materials losing their moisture to the environment around them as opposed to vice versa. Now, relative humidity, we've got the percent saturation of air based on the current temperature and dew point. I hope most of you that are joining us probably were in for the last webinar. If you weren't, please do feel free to look that up online. But that was our discussion of the relationship between temperature, relative humidity, and dew point. And this graph below, or the figure below that you're looking at, is going to give you a little bit better idea of how that relationship works. But what we recognize is that at a constant dew point, as the temperature goes up, the relative humidity goes down. And as the temperature goes down or it cools down, our relative humidity in the space is going to go up. And we actually use this as part of our experimental protocol, and you'll see how that played out here in just a few minutes when we get to those slides. Now, preservation concerns, again, just a quick overview from what we've discussed in the past. If we've got dry conditions, well, it's not all bad, if you will, right? That's actually good for the rate of chemical decay. The less moisture is present, the slower that rate of the chemical reaction. But the concern is that for a lot of our materials, as we remove too much moisture from the object, that can have a severe negative impact on the physical construct or on the physical dimensions of the materials that we're working with. So the possibility for mechanical damage in terms of materials becoming desiccated and slowly cracking, or just truly changing shape into a permanent disfigurement of their original self. We're concerned that that's going to be the end result if we have overly dry conditions. Now, again, if we look at mold risk, here we are, dryness isn't a bad thing, right? Our goal for mold is to stay below 70% relative humidity, and the drier we go, very much we have a reduced risk in highly unlikely scenario where mold is ever going to terminate. So best practices for dry conditions, what is it that we want to stay away from? Well, we certainly want what we would describe as a moderate moisture content within our preservation environments. And for most materials, this will equate to about a 30% relative humidity condition as the driest that we would want to go. For book and paper, for most typical library and archives collections, 30% is an acceptable minimum. Now, if we're dealing with sensitive objects within those collections, if we're dealing with collections of parchment or vellum or weakened leather, then by all means we probably want to keep the relative humidity a little bit higher, and 35 to 40%, and many people will use 40% RH as a minimum condition for storing those particular materials. And again, to take it a little bit further and now thinking about the larger museum world or even the world of different historic preservation projects and what we're thinking about oftentimes with outside collections or outdoor collections. For stones and metals and ceramics, dryness, the primary approach here is the 20 to 30% for many inorganic materials is still perfectly safe. Lower than that, we can begin to cause various different types of decay with certain inorganics. Damp conditions, as we said before, this is a reality for much of the world as we go through, not only seasonally in different parts of the U.S. and Canada, but also as we get into tropic and equatorial regions, we have severe issues and problems with dampness year-round. To move through, what is it that we're dealing with? Where does this come from and what does it cause? Well, if we have moisture, damp outside air, humid outside air, high relative humidities to begin with, then much of that is eventually going to make it through our building. If we don't have the right vapor barriers in place or the right mechanical systems in place to combat that, then we have to accept that oftentimes the indoor environment will look much like the outdoor environment. On top of that, if we have precipitation or a lot of rainfall in a particular area, the soundness of the structure, the soundness of the roof, any groundwater that may come up through the base of a building or up through a basement. And beyond that, just dealing with standard building maintenance type of issues such as water leaks, condensation in various conditions, and even surface or ground moisture that may come up against the side of a building. All of these can lead to periods or to prolonged periods of high relative humidity and damp conditions within a particular structure. And is there any time of the year or any particular type of decay that we're good with in terms of high relative humidity? No, we've gone through that before. But the reality is the higher the RH, the faster the rate of chemical decay. The higher the RH, absolutely, the greater the risk for mechanical damage. We're going to see expansion of materials beyond their normal physical bounds. And beyond that, we can see some other general disfigurement of material as we start to increase the moisture content of any hygroscopic material. And even on top of that, we've got the mold risk concern that, again, the risk increases at 65% and above, and it's at 70% really that we start to see most of the germination and problems occur. So there aren't a whole lot of acceptable scenarios where we're good with high relative humidity conditions. And to kind of define those, most of the time we can mitigate this damage by keeping the RH below 55%. Once we start to go above 55%, we start to introduce problems having to do with metal corrosion and oxidation of different materials. Anything above 65%, not only are we thinking now about mechanical damage and the expansion of materials, but we're also starting to get into that mold range where we're concerned with 70% relative humidity. Just to keep in mind, again, to revisit that whole idea of if we have a constant moisture content within a space, keep in mind that if we lower the temperature at a constant dew point, then the relative humidity is going to go up. So when we're talking about mechanical control of buildings, if we take that condition and the system is only capable of doing a certain amount of dehumidification for you, lowering the temperature on that system or lowering the set point temperature of the space in many cases is going to have a net negative impact for you. You may slow down the rate of chemical decay by dropping temperature, but if you, shall we say, inadvertently raise the relative humidity of that space by dropping temperature, then you're going to introduce a whole lot of other problems just by raising that RH beyond what would be the normally acceptable moderate ranges. Just for a little bit of comparison, and this is really just to kind of give you an idea of what the differences in terms of moisture are that we're talking about. We take this nice, beautiful, I don't know if that's technically Victorian, I'm not much of an architectural historian, but we take this nice historic house, right? Without forced ventilation, just kind of exists in the environment that it's given, and we accept that moisture contents inside the house are largely going to mirror what the moisture contents or the RHs are outside of the house. What we know is that for typical construction, we're going to see about 1 air change total volume in the house per hour, just through infiltration, just through coming in through windows, coming in through the roof or through doors, just moving throughout the structure of the house. Now, if we take that historic house and plop it down in the middle of Savannah, Georgia in the U.S., and just on a nice, hot, humid summer day, we're going to see about 98 gallons of water that will infiltrate through that house in the form of water vapor. And I think any way we look at it, that's a lot of moisture that we're dealing with in terms of what is coming in from the outside air. That said, if we take that same structure and we plop it down in the middle of Henderson, Nevada, nice, dry, arid, although still hot climate, low relative humidities for much of the year, over the course of a day, we're going to have about a gallon worth of water coming in through that house. So this is, the idea here is just to recognize that the structure has sort of this base introductory buffering capability, but if you will, it's not very much. Don't necessarily take it for granted if it's not built to be that way. In this case, the historic house, which is maybe the object that we're trying to preserve, is going to have a lot of moisture moving through it just by means of its normal construction. Now, different materials are going to be at risk for different reasons, and the amount of risk that an object is going to be at from either dry or damp conditions, those high RH or low RH conditions, is really based on 3 primary characteristics. We're dealing with the nature of the material itself, what is its history, or what is its provenance, where did it come from, where was it created, how long has it been there? And finally, what is its own composition? You know, how is it formed? And that goes beyond just the straight nature of the material. But when we think about the nature of objects, you know, oftentimes the first thing that comes to mind is it hygroscopic? And keep in mind that hygroscopic materials are not simply organic materials. They can primarily, oftentimes we think of them as organics, right? But, you know, for organic materials, these are items that are, you know, made of wood bases, carbon-based materials, oftentimes plant, but it also includes everything from leather and horn and bone to ivory to any sort of plastics are organic, some of which are hygroscopic. Actually, most of which, I should say, are hygroscopic. But when we think about it, those are the common ones that we're dealing with in library and archive settings. But the flip side, and the other one that we have to consider, is that there are a number of inorganic materials that are still hygroscopic as well. And even though we might not think about it in terms of what is the potential for damage to these objects based on high moisture content, you know, oftentimes we'll think about it in terms of, well, if I have metals, they may corrode. We may have oxidation issues. But this also goes to the idea of what is the effect of moisture traveling through a particular hygroscopic yet perhaps inorganic material. Are we going to start to see efflorescence of salts or efflorescence of minerals on the surface of buildings? Are we going to see different impurities or different additives to materials being brought to the surface based on changes in relative humidity in a particular space? And that's what we have to keep in mind and think about as we're looking at the overall collections and the content that we have and how they might react to changes in moisture content and changes in RH in the surrounding environment. The provenance and the history of the material, it's an interesting thought, and oftentimes it's a hard one to nail down and really identify, if you will. But the simple reality is that materials and the materials that we're working with have a memory in terms of what they've been exposed to in the past. If they were originally created or housed and formed inside of a dry climate or maybe a particularly damp climate, then they may already be, if you will, fully equilibrated to those conditions. And a dry environment or dry condition may be perfectly acceptable to, say, ethnographic materials that were created and have lived most of their life in the American Southwest. By comparison, if you'll take ethnographic materials that were perhaps formed or created in equatorial Africa or even different parts of Central and Latin America, what you may find instead is that as you bring these materials that were first equilibrated to very damp conditions and are used to quite a high moisture content and high relative humidity, and we've seen time and time again that when you bring those to institutions in the United States and Canada and throughout the world and put those in an environment that may have seasonally dry conditions, and specifically those environments where we have difficulty controlling winter relative humidity levels, and we start to see particularly low relative humidities throughout the winter months, then what we know is that those materials that have been already fully equilibrated and formed in high RH conditions are going to be particularly sensitive to those low RH conditions and may actually begin to show damage and show physical damage far beyond other materials of like structure or of like material may show that were created in a different part of the world or that were formed in a different part of the world. And finally, when we think about the composition of an object, it's not just its own sole nature, but it's also what has it been joined with, or what has been done to it, or what shape has it been created within. And this comes down to different types of composite objects that can range anywhere from modern museum pieces to the very typical paintings and furniture and musical instruments that we see. You can see the ivory coming off of the keys on a piano in this case. The impact of dryness or dampness or moisture levels on these different objects is essentially that different materials will take on moisture or give off moisture at different rates. And if we have materials that are joined by an adhesive or are joined together in a particular object, where that adhesive takes moisture on and gives it off at a different rate or can chemically fail over time, not to mention the physical expansion and contraction of the materials surrounding or that are attached to that adhesive, over time we begin to see that connective layer, that adhesive layer fail. And you may see materials that are pulling on one another or exerting stress or force on a joined material that, that other part of the composite may not normally feel. Anything that is solid wood or ivory, where we have a large material that maybe doesn't have a good place to relieve stress, as we see that expand and contract with moisture content, it's going to choose the weakest part along that construction to fail oftentimes. And we may see it in the case of this drum here in the lower right, but also when we look at carvings and think about why is it that they fail and where they fail. You think about that weakest point, and oftentimes different cultures and different artists have taken to actually creating what they call stress relief or relief cracks within the back of materials or outside of where the artistic interpretation is supposed to be taken from, so that if the material fails due to mechanical expansion or contraction, that it fails in the place where they want it to. And finally, when we think about stretched materials, whether it's hide, canvas, any type of, when we're looking at ethnographic material, but also if we're looking at even paintings, we can see failure of that stretching once it's been placed under stress, and we see the physical expansion and contraction due to moisture changes. All right, let's get into the meat of it. We've spent enough time in the background. So I want to go through here for a little bit and just give you an introduction to the research that we've done. And as I said previously, this is by no means the full breadth of research that's available out there in the professional field. But over the last 20 years or so, we've had a lot of experience and a lot of opportunities to look at the impacts and the rates of equilibration, the impact of enclosures on those rates for a number of different media types. And what I really want to talk about today and think about is, for library and archives collections in particular, which is for what most of this information and data is based from, that we can learn an awful lot in terms of how quickly these different processes are going to occur. And largely we have data that maps very well with film, paper, archival materials, books, photographic materials. And we want to use that just sort of an introduction or a means to kind of get some perspective on what these processes look like. And I do want you to keep in mind, I do want to caution that what we're going to talk about today in terms of rates certainly does not apply to not only every material that we may have in our institutions, but it also doesn't apply to every storage scenario that we may have materials in. We're going to talk an awful lot about thermal masses and a lot about dense collections of materials. And please do keep in mind that as we're talking about rates of equilibration for some of these different arrangements, it's going to be very different if you have a single object that's laying out on a conservation bench or laying out on display in a particular exhibit in terms of how quickly that particular material may equilibrate to its surrounding conditions. So do just kind of take that as a caution or a precaution as we move forward and talk about this. I want you to take the information for the value that it does have and make sure that we don't try to take it too far. So to start out, our introduction to this particular field and area, and I want to say that a lot of this research at IPI really has been done and driven by Jean-Louis Bigardon. Here he's one of our primary researchers at IPI, and he's worked in various aspects of this over the last 2 decades. But the original study, this 1994 project, was really focused on what is the effectiveness of different enclosure figurations for different types of film media. And we were looking at a couple of things. Not just what the rate of equilibration was for film in various environments and various conditions and how quickly it adjusted to temperature and relative humidity changes, but were there particular enclosure recommendations that we could make in terms of, if you will, in this case, different types of film canisters or different types of containers that would slow those rates of equilibration and provide a better internal preservation environment, if you will, a microclimate or microenvironment for these media compared to the overall external room or macro environment condition. And what came out of this really were some practical recommendations for the preservation of cellulose acetate and photographic film. And the fascinating thing here, maybe it's not necessarily that we expected anything different, but a lot of the findings from this came down to the fact that temperature equilibration for any type of housing, for any type of enclosure, was relatively fast. This is where we first started to find that data that temperature equilibration happened largely within a number of hours. But as we started to look at different enclosure materials, when we started comparing metal film cans to plastic film cans and other different types of open or different types of available housing that are common for film storage, what we were finding is that absolutely the best possible scenario was to use what was at that time largely new film containers and film cans for long-term storage. Plastic film containers and film cans, sorry, I think I skipped that part. But to use those because they did significantly slow down that rate of moisture equilibration. Metal cans were also effective, but for whatever reason we didn't see quite the same seal. There wasn't quite the same, if you will, air seal from the microenvironment inside the can to the macro environment outside. And the equilibration was just a little bit faster. And other materials that we were trying, cardboard boxes, different types of plastic containers or plastic film cans with an air gap or metal film cans with an air gap, just allowed the interior microenvironment to change equally as rapidly as the exterior environment. And you lost that buffering capacity, or you lost that buffering potential or benefit of the different media. Move that forward to 1998, and at this point we're starting to look a little bit more at, all right, well, not just equilibration rates, but if we think about the actual rate of chemical decay and what it is that impacts that rate, then how is it that fluctuating temperature and relative humidity might change the rates of chemical decay, or how do we think about this, what at that time was arguably, and I think in many cases still persists, this notion that it's the fluctuation of temperature and relative humidity that is damaging, and where we would tend to lose track of the idea that it's the extremes that do the most damage. And that was part of the test, was to say, all right, well, let's look at it in terms of what does the extreme do, and what is it that these regular fluctuations do in terms of total decay and damage. And what we found, what the takeaway from this particular project was that cycling behavior, that normal fluctuation or that tested fluctuation of temperature and relative humidity in and of itself was not inherently detrimental or not inherently damaging to the overall rate of chemical decay. It really came down to what the actual condition was and how long the material spent at each of those conditions, and to go back to the 1994 research, whether or not the materials were able to fully equilibrate to those various conditions that they were exposed to. In the end, to put it very simply, it was the temperature and relative humidity level, or the condition, that mattered in terms of the rate of chemical decay, far more so than any impact of just natural or normal cycling or fluctuation. Thinking about that and some of the measurements that we were able to take from that particular study, and that recognition, one of the things that we found was that full moisture equilibration really just flat out takes time. If you look at the core of the material, let's take a hardcover book just sitting on a shelf, no particular enclosure, but for that material to reach 90% equilibration at its core for relative humidity, that took 1 month in order for the core to feel 90% of the total change. Now, you take a reel of 35 millimeter film with no enclosure, that would fully equilibrate over 2 weeks. Not as much thermal mass, it equilibrated much faster. Maybe depending on dimensions and size of the hardcover book, maybe there was a little bit more surface exposure to work with. Now you take that same 35 millimeter reel of film and you place it in a metal can, that rate of equilibration, or the time it takes to get to 90% equilibration, changed from 2 weeks to now it's 6 months. And similar in comparison, you take a 2-inch data tape, boy, remember when we still dealt with those an awful lot? You take a 2-inch data tape and you put it inside of a plastic container, and to 90% equilibration, that also took 6 months and upwards in order to reach there. So it really does give you a feel not only in one case for just the type of material that we're working with between the book and the bare reel of 35 millimeter film, but also looking at the impact of an enclosure on that rate of equilibration, or on the time that it takes for material to equilibrate, and the impact that that metal can and that plastic container had on how quickly the film and data tape equilibrated. Now, fast forward, give or take about 12 years, as we kind of let that equilibration study, we felt like we had done it and worked with it for film. That was our primary interest and concern at the time. Fast forward to 2010, and at that point we were starting to get a lot more interested in thinking about sustainability. And what is it that we might be able to think about or take advantage of in terms of different operating approaches or different understandings of how materials live and coexist with the environments that surround them. And John, we went back again and had this idea of thinking about, well, how is it that we might deal with or approach the thinking of equilibration rates and the use of those and the use of setbacks to approach something that is both beneficial, or at least not having any negative impact for the rate of preservation, but also looking at it and saying, is there a way that we can save energy here? Is there a way that we can think about a setback protocol, maybe changing temperature, changing relative humidity on purpose, and using that for energy sustainability, for reducing energy consumption? But does that work because of equilibration rates? We have this thought from the film study that it's going to take a while for most materials to equilibrate. Well, can we use that to our advantage? Can we do that on purpose? So that was working with that presumption. Let's take that and think, if we're not harmed by these short-term environmental fluctuations, then gosh, what's the impact of that, and what's the benefit that we could see at the end of the day? So there were a lot of questions that kind of went into this. There are a lot of things that, what is not only laboratory testing, what is something that we can research here at IPI, but what is also some field research that can be performed? What is it? How do we deal with this in real-life practical situations? One of the challenges was, how do we evaluate the impact? How do we know what it is the object felt as a result of these short-term fluctuations that we might purposefully cause? And another question that came up is, how do we define safe? How far can we push that envelope? And where is the limit when real damage is done? And I'm not entirely sure that we came to a final answer. In fact, I know we didn't come to a final answer as part of this study, but it actually inspired some more questions. And we're working on another research grant right now on looking at surface changes in materials based on relative humidity conditions. So that's looking a little bit further into that. Where does the real damage occur? One thing that we wanted to do and think about was, this is purposeful. This isn't just what happens by accident as a result of how buildings respond or what happens outdoors. but this is an intentional change that we're going to put in place for testing purposes that might mirror or might look like something that institutions would normally try themselves for the purposes of energy savings. And that might include an HVAC shutdown. This was related to the shutdowns research that we also did at IPI during this period, but also looking at just setback conditions. What happens if you don't turn the system off, but you just change the temperature or the relative humidity set point? And that's both on a short-term, nightly basis, but also on a seasonal basis. Elements, I think I mentioned these just briefly, but a lot of this was lab research that we did here at IPI. Some of it was field investigation, and by field investigation, I mean we basically went across the academic quad here at RIT. We didn't have to go too far. We went over and worked with our partners in the RIT libraries to test how it worked in their particular building using the normal building operation at the Wallace Library. And finally, looking at the data analysis and thinking about, what can we recommend in terms of behavior, control, or operation of HVAC systems based on what we're seeing in these rates of equilibration and how the cores of materials react to these environmental changes. So we studied a number of different configurations. We looked at books, we looked at photos in a stack, different matted photographs within a box, within different types of boxes, and stacks of paper that were meant to mimic if you will, records or archival collections that were stored in a number of different housing options that you might find in any typical repository throughout at least the US and the rest of the world. So these varied by and large, and as you'll see here in just a moment, well, we'll get there in a second. But once we had all these materials, all of our different test subjects prepared, well, what did we put them through? A number of different profiles. We were looking at, all right, what happens when we actually go through and decrease the temperature? What happens to the relative humidity? What happens when we increase the temperature? Not just, we know what's going to happen to the relative humidity, but how does the object respond to it? What happens when we decrease the amount of space or decrease the total volume that this entire experiment is happening within? The idea here was to say, you know what, instead of having a book or a series of books on a shelf inside of a big room, what if we try to mimic this idea of high-density storage in a lot of our archives and library repositories and increase the total volume of collection material to the total volume of available space? In other words, let's have a lot less air circulating through this space and a lot more of this area taken up by collections materials and see what happens. What happens if we make it a bigger space? And finally, what happens when we start looking at different conditions that we purposefully adjust the RH levels and try to control those rates of RH change in equilibrium? What is it that the objects are going to do? So to start out, here's a typical profile. This is at a constant dew point, and I will say for everybody who's listening in the US, all of these graphs are in Celsius, so you'll see the temperature scale over there in C. But at a constant dew point, this just shows us that normal relationship, that as we increase the temperature, I'm going to use a cursor here to point this out, as we increase the temperature during one cycle, the relative humidity in that space changes correspondingly and decreases. So this is a normal environmental profile. This is what we expect to see. Notice that this temperature increase is quite substantial. This is probably more than a building would experience on its own. But we're doing this in a controlled laboratory setting to try and see how it is that materials will react. Materials that we used, how do we put this together? Let me tell you, several people spent an awful lot of time carving little holes out of books so that we could get the data loggers and the sensors into the space. No significant collections materials were harmed during the course of this project. I will say a thank you to several local repositories that donated some of their weeded and otherwise being discarded materials to this effort. But as you can see, inside of our chamber here at IPI, we had a number of different materials and different enclosures with loggers inside of each of those arrangements. And typically we were logging in 3 different areas. We had loggers in the macro environment in the room itself. We had a data logger inside of the box in what we call the micro environment that would register the impact of the box on the change between the exterior room environment and the environment just within an empty space inside of the container. And finally, we had a logger at the center, at the core of the material that was inside the container. So we had this stepped approach to try and see what it was, what the impact of each of these different variations was. what was the condition in the room environment, how much impact did the box or the container have on rates of equilibration, and how long did it take the core of the object itself to feel the purposeful environmental changes we were doing. So if we took a stack of matted photographs inside of a cardboard box, when we changed the temperature in the macro environment, here, this is the ambient condition on the red plot, here's our normal temperature change. Well, what did it feel inside the box? What was the impact of that box on the rate of temperature equilibration? The answer, not a whole lot. Here we are really within a couple of hours, that micro environment inside of the box felt the entirety of the temperature change that occurred in the micro environment and just continued right on. So this was just one bit of documentation for when we're talking about a cardboard box with not a very good air seal, is there any impact at all on the rate of temperature change? The answer is very, very little. Now, however, if we take that same cardboard box with a stack of matted photographs in it, we start to look at the relative humidity change in that microenvironment, in other words, in that open space inside of the box, compared to what's going on outside of the box. Now's where some of the interesting stuff starts to happen. If you remember back to that graph a couple of pages ago, when we were looking at that normal profile, that as the temperature went up, here's our temperature increase in the macro environment. Actually, this is inside the box, but as the temperature increase in the macro environment went up, it would look very similar to this curve. We expected to see the macro environment RH go down correspondingly, maybe something looking if you follow my cursor. But instead, when we look at the microenvironment, the impact of the box, we started to see a couple of things. First, that immediate temperature increase caused this first initial spike of relative humidity inside of that microenvironment in the box. And as time went on, we see that it does start to change with the RH relatively quickly. We didn't ever get to the full RH equilibration that the macro environment felt, but the RH change was nonetheless fairly rapid. And if you go a little bit further down here in the graph, notice that by the time we spent, give or take, about 24 hours worth of a period of change, that full RH equilibration inside of the box was felt. So fairly quick, right? But there is a little bit of a delay, a little bit of a buffer going on. But let's talk about these spikes just initially. And the interesting thing that we found was that the initial temperature increase, followed here by that temperature drop, were driving some of the moisture relationship inside of the box. That temperature increase would cause the material to give up some of the moisture that it contained, and that moisture would go into this empty airspace inside the box and raise the local relative humidity for that space for this short period of time before everything started to even back out. The material actually took back on a little bit of that moisture, and we see the temperature going back down, with the opposite here occurring when we drop the temperature in the space again. Now, to go back just to thermal equilibration, looking at enclosure types, is there really any enclosure that we can use that is going to slow down this rate of thermal equilibration? And the answer for what we were looking at in our satisfaction, the answer is by and large no. If we look at the ambient condition here in the teal line, and I realize that these can be a little bit difficult to see, but we have the ambient condition, and then we have two different types of enclosures. One here is just a cardboard box, just your standard metal edge box, but the other is a museum case. This is a far better sealed, a far more dense, solid case, if you will, that we placed similar material inside, and we were looking to see, all right, what is the impact of the container itself on how quickly that temperature change is felt? The answer, very little impact at all. It really didn't matter what type of enclosure, what type of case we were using. The temperature change inside of that environment was felt very rapidly. And as we tested this throughout a number of different scenarios, the answer kept coming back. The enclosure itself has very little to no impact on the rate of temperature equilibration inside of that container. Now, looking at enclosures in micro relative humidity, or looking at relative humidity within the enclosure, we do start to see that the enclosure can have an impact on how quickly the RH change is felt inside of the box. So here we are again, trying to find my cursor, sorry about that. Here we are again dealing with the ambient relative humidity, and notice here we're working, here's our normal condition. As the temperature goes up, the RH goes down. And notice the blue plot, this is our standard cardboard box, that It doesn't feel the entirety of that RH change, but it does get a fairly good portion of the way there, maybe 50% in the microenvironment. But as we look at that museum case, notice that there's far less change in that interior environment in terms of RH. It doesn't feel anywhere near the total change in RH in the macro environment. Maybe in this case, we're looking at about a quarter of the total change for each adjustment period. So there is data here that was telling us that, you know what, the quality of the case, the density of the case, the seal on the case, in this case a museum case compared to a cardboard box, does have an impact on what that microenvironment relative humidity might be. Now, it's still felt as a result of the temperature, these slight immediate spikes of RH inside the case and then drops and lower drops inside the case of RH when the RH went back up and the temperature went down. But we are finding by and large that the container can have an impact on what that microenvironment and the material feel in terms of RH and how quickly it equilibrates. We'll go a little bit further, and this is where we're actually going to get to the material core. So this is actually a good illustration of that arrangement. Here's the logger in the ambient condition just sitting on the cart. This is that logger inside the microenvironment, and this is that museum case that we were talking about just a moment ago. But here's the microenvironment condition, and finally, here on the inside of this matted stack of photographs, we have the embedded logger. And the embedded logger's job is to measure this small air pocket and how long it takes, or whether it ever gets there, for that air pocket to feel the same change as what occurred out here in the macro environment. And that's what these three plots are comparing. So if we go through and look at this ambient condition of RH, this is our normal pattern. This is our normal experimental design, if you will, whereas the temperature went up, the relative humidity went down, and we see this normal, if you will, almost a day-night pattern that we are imposing on that particular space. So we have the fluctuation that occurs normally in the space in RH, and then we have just right here inside the museum case, this logger is the blue plot. So here's our microenvironment, and notice that it does start to finally, as we go on, it goes down, down, catches up a little bit each day with that RH drop. Over this 24-hour period, gets significantly further. And notice that we kind of reach this equilibrium point, give or take, I'm going to say right about here, maybe a total of 2 weeks in, give or take, is when we start to say, all right, the inside of the case right here has reached equilibrium with what is going on outside of the case. We've hit this nice flat level of what is going to be that equilibrated condition of varying conditions in the ambient space. But if we take the core condition here inside the material, notice that as we start out, notice how long it actually takes that material to catch up with what is going on. Here we are at 2 weeks. We still are not fully equilibrated to just what is happening inside the case itself, let alone what's happening in the external environment. Keep going. Here we are at 3 weeks. We're getting close. And really, where we hit it and we're really starting to match and say, all right, everything is now feeling roughly the same condition, is about 1 month into the test, is where we start to say, all right, the core material, the core of the material, this space inside the center of the object, is feeling the same condition as what is going on here to the exterior. And that just tells us that how slow it is, how slow that moisture change is throughout the full, if you will, dimensions of this particular object. There's enough mass here that as the moisture is moving in and out of the object based on changes first in the ambient and then in the micro, that it takes a long time for those moisture changes and for that full equilibration to be felt here at the core of the material itself. So to sum it up, what did we learn? What were we able to take away from this? Well, the first part is that the temp increase in the material surface, that was kind of fascinating, right? Initially, when we increased that temperature inside in the ambient environment and that temperature change was felt inside of the container, it caused that short-term desorption. As the temperature of the object went up, then it released some of its moisture into that microenvironment inside of the box. And the fascinating thing there is that we start to realize that that moisture diffusion, i.e. that given that desorption of moisture from the material inside the box, was able to, for even a short period of time, control that microclimate, right? We saw the microclimate RH go up as a result of the object releasing moisture responding to that temperature change. Now, at the core, what happens? The temperature controls the moisture. So as the temperature increases, what we're thinking about is as the temperature increases, we're actually promoting that moisture desorption and the RH increases. So that sudden temperature change, what are we thinking about? Well, it causes moisture transfer. So this leads to, how do we think about this in practical terms? If we're working in a building, or if we're working in a particular environment where, keep in mind, oftentimes what changes fastest, the easiest thing about a particular air condition to adjust is its temperature. Moisture control takes a lot more work and is typically a much slower process. So if we have a temperature change that happens fairly rapidly, then are we going to see cases where, as a result of that temperature change, materials are going to desorb, or as a result perhaps even adsorb moisture and take it on simply as a result of changing temperature conditions, not even looking at vapor pressures, not even looking at normal transfer of moisture across objects and across surfaces? And I think we'll be able to take a little bit more information from that in a second, but I want to wait until we actually illustrate that. So here we are. We're going to hone in on that for a second. This is testing inside of a sealed environment. So notice, if you see the white walls, this is our walk-in chamber here at IPI. So we've taken this, I don't know, maybe 10 by 10 room and created this smaller sealed, I think in this case we're dealing with acrylics, but dealing with this smaller enclosure inside of that space. We want to try and increase the proportion of material in the space to the availability of air in the space. And what starts to happen if we have that sealed environment? What do we see? Well, we find that the materials, based on these temperature changes, will control their own micro RH inside of that environment. We see that the materials start to take over. So using our loggers again, here we are. This red is the temperature at the core of the object, and at blue we have the temperature of the free space. So if we change the temperature in the free space, notice that the temperature of the object changes relatively quickly, right? There's not a whole lot of buffer time there. It equilibrates very rapidly. But look here at the relative humidity graph, and I understand that these lines are light. I hope everyone can make them out on the screen. But notice for the significance in the temperature change, that's 5 degrees C, that we see virtually no adjustment, no fluctuation at all in the relative humidity condition. And this is, looking at this and trying to explain what's going on, this is that loss, this is that giving up of moisture from the object to the surrounding environment, where we would expect the temperature to go up and a corresponding drop in relative humidity below this particular RH level. Instead, we see the RH stay level, and it's because the moisture is giving up enough moisture to the, or the object is giving up enough moisture to the environment that the RH can stay level, even though the temperature has changed and would normally drive the RH down. And this was shown time and time again, not only in this experimentation that John Louis was working with, but it also came out in the shutdown experimentation that we were doing in institutions, whereas we would look at spaces, especially high-density storage spaces, where there's a lot of mass and a lot of material present compared to the total air volume of the space. What we found time and time again was that even when we saw temperature fluctuation by shutting down a mechanical system at night, oftentimes there was very little change, or at least far less than what we would expect in terms of the relative humidity condition. And in some cases, we saw a little bit of impact simply based on temperature. But in other cases, I suspect, and even though we don't have the sheer data to prove it, but I suspect that we're seeing something very similar to what Jean Louis found in this controlled environment, which is that as the temperature fluctuated, either went up or went down, the corresponding moisture release or absorption by the materials in the space were helping to level out and control the RH condition within the environment. So we do, I think the evidence is pointing in the direction of seeing that the materials truly can take over their environment based on what those temperature and moisture contents happen to be. Now it's hard. I don't think we ever found a break-even point of just how much material did it take in order for this reaction or in order for this relationship to hold true. But that's something that maybe we could look at in the future and think about, well, what does it take in order, how much mass do we have to talk about in order for a collection to control in many ways its own environment during these short-term fluctuations. So to take that a little bit further in a field experiment, some test samples that we used over at RIT, we were dealing with books just in a normal stack on a shelf, the way any the way any university or circulating library would typically arrange a book collection. Paper stacks in cardboard boxes, photos stacked inside of a cardboard box, matted photos stacked inside of a cardboard box, and finally reels and microfilm on the shelf. Now, the interesting thing about RIT's library is that there's a whole lot of stuff going on in terms of environmental control in one building. And as we went through and started thinking about what it was that the different parts of the library were doing for mechanical control, we found that really there were 5 total zones that the library was dealing with. We had one zone in the building where they set back for 6 hours at night. And really we're looking at different seasonal conditions and what it is that they would be holding for seasonal environments. But the HVAC could be off for up to 6 hours at night every night of the week. In this case, I think that was actually just weekdays. But if we look at another zone, we have no setback at all. The mechanical system ran the entire 24/7, 365 days a year at a flat line, steady temperature of 21 degrees Celsius, or about 70 to 72 degrees Fahrenheit. Another part of the building was shut down for 8 hours at night with seasonal set points again, and another not only had shutdowns for 8 hours a night, but actually had different seasonal set points. The system itself was being operated differently beyond simply the schedule. And finally, there was one section of the building that had no varying set point and frankly not a lot of control at all, but tried to hold really as flatline temperature and relative humidity control as best as it could that was just turned on all the time. It was one of the few parts of the building that had relative humidity control in this particular circumstance. Now, what do we start to see? What do we find? And this is looking at those macro environments again, and I realize we're taking 2 different views here. We've got over here a temperature graph just looking at ambient conditions. This is Zone B and Zone C, 2 different parts of the building over at RIT's libraries. So notice in this particular case, we've got one space that has these nightly shutdowns or these nightly temperature fluctuations that they're dealing with. Not a whole lot of fluctuation there. By and large, even less than a half a degree Celsius per night, but the fluctuation is there. And we also see the same in the other zone where the temperature would drop a little bit during the night. But if we look over here at the comparison of both temperature and RH for those ambient spaces, what we want to point out, or what is critical, is that even though we held this relatively flat line temperature condition, and this is running from August of 2011 to March 2012, so a little bit more than half a year when we look at it totally. Even though we could hold this very nice, literally flatline temperature condition with a little bit of nighttime variation, what we find is that seasonally, the RH in these spaces drops significantly, right? We go from working with an RH in summer of probably between 50 and 55% down to RHs that drop as low as 20% in the wintertime in both of these zones. And that's a challenge. There's a lot of temperature control there, but very little control over moisture in the wintertime. There's no humidification capability. And when we placed a book in those particular environments, what you find, and I'm sorry that these graphs aren't on top of one another, it's a little bit hard to get everything fitting on one page. But what you find is that what the book felt, temperature-wise, was exactly what the exterior environment was doing, exactly what the ambient environment was providing it, which is this nice flatline condition, and it showed a little bit of those nightly perturbations in terms of small amounts of fluctuation, even at the core. This is the core of that book. But notice, and I'm going to go back, bear with me one moment, I want you to see the fluctuation in RH just on a daily and sometimes even less than daily level. But see how much, as that RH is dropping over the course of the season, you see the fluctuation that we're dealing with and how much it might go up or down based typically on moisture contents outdoors. This would model probably very closely, if we looked at dew point, it would model very closely what was happening outside in Rochester. But if we look at those relative humidities inside of the book, notice now that they're much flatter. And not only are they much flatter, but it doesn't get to nearly the dry level that the exterior environment does. Here we are on November 1st, and we're already feeling 30% relative humidity in the ambient environment. That's our low limit, right? For these collections, we don't want to go much lower. The rest of the season is spent going lower than 30%. But here we are inside the book, And as of November 1st, we're still sitting up here at about 36 to 38% relative humidity, and really doing okay in terms of moisture content or RH levels inside the object itself. Now, again, keep in mind that we're talking about the core of the object here. It is highly likely that the surface of an object, if it were exposed, has felt most of the equilibration to that external condition. And as I said, that's part of the research that we're working on now to look at the RH impact of surfaces of book and paper materials. But in terms of the rate of chemical decay and the impact of fluctuation on chemical decay, then what we're seeing is that the core of the object hasn't equilibrated all that rapidly to what is going on in the ambient surroundings. It's moving along at a much slower rate. It probably doesn't have a lot of surface exposure in this case because it's surrounded by other books on a shelf, and the two of its 6 surfaces, the 2 largest ones, are going to be largely covered up by other books. That's the great thing about that particular book arrangement, is that you reduce the surface area exposed of each individual object. So that's an interesting takeaway in terms of, all right, the book is moving much more slowly. The equilibration rate for the center of the object is fairly slow, even though the ambient environment doesn't have a lot of control. So where did this take us is this idea and the thought of, well, what can we do with microclimates? And I think what we're taking away from this is that microclimates can really govern rates of decay. We can take an environment that is able to be controlled to a better level based on buffering, based on some level of dealing or mitigating the conditions that happen around it, and can give us this small microclimate of temperature and RH that can be not only a much, shall we say, smoother or buffered condition, but where we can avoid these extreme danger conditions for a longer period of time. Not to mention the fact that if we can do that, if we can achieve this smoothing out of that rate of that change of the amount of time that is spent at those extreme conditions, then this gives us opportunities to think about intentional system operation to try and reduce energy usage or energy consumption, and looking at sustainable solutions. Now, what to take away from this as we think about, all right, what can we put in place for sustainable operation and strategies, is that a lot of what makes this possible, or a lot of what makes this accessible or reasonable in terms of looking at preservation, at least in terms of chemical decay, is that these equilibration rates oftentimes work in our favor. When we're talking about shutdowns, or when we're talking about setbacks of library and museum HVAC systems, where we're going to be off, or there's going to be a fluctuation for, call it 8 hours a night in various situations, then what we have found is that over the course of that 8 hours, based on this data, over the course of that 8 hours, the materials are going to equilibrate to that temperature change fairly rapidly. And at the end of that 8 hours, if you had 2 degrees fluctuation in a particular space, most of the material probably felt that full 2 degrees worth of fluctuation based on the material within anywhere from 5 to 8 hours of that change being made. Now, that being said, over that 8 hours, did the material feel any change in terms of moisture content or in terms of relative humidity? The likely scenario is, at least at the core of the object, or for the vast majority of the object, absolutely not. When we're looking at these core conditions and looking at equilibration times that take upwards of anywhere from 4 weeks to even numbers of months based on the density of the material and the type of container that it's living within, then what we're finding is that these short-term 8-hour fluctuations that are designed for energy savings have very little impact in terms of the total RH condition of the object. The object itself takes a long time to feel those changes. So here we are. Enclosures and cabinets can, I guess I just said that, can prevent equilibration to the worst of summer RH, and arguably also to the worst of winter dryness as well. Right? If we can block that air exchange, if we can reduce the flow by which moisture gets into and out of a particular container, then it's going to make a difference. Now, to look at these 2 different arrangements, what do we expect? If we have a sealed cabinet with gasketry that is going to not allow a lot of air exchange at all from the external ambient environment here to the internal microenvironment, then these materials are going to see a very slow rate of equilibration simply based on the buffering provided by that cabinet. Now, we – folks, bear with us for just a second. For some reason, we've lost some of our audio. Okay. Sorry about that. There was a slight glitch in the audio. It sounds like maybe you might have missed me for a minute. For anybody who jumps in and reminds us of that, thank you. But just to continue, what we're talking about over here on the right-hand photograph is looking at these metal-edged cardboard containers and at the graphs we were inspecting earlier. You know, what it comes down to is these don't provide a lot of buffering. They provide virtually no buffering in terms of temperature. But because of the air gaps that are sort of a natural part of this construction, moisture can rapidly move from this exterior ambient condition inside of the case itself and can begin that equilibration process with the material all the more quickly. So if we're looking at considerations or looking at problems where we have very high RH, summer high RH issues or very low winter RH issues, we can't rely just on these standard containers to provide any sort of buffering in terms of that rate of RH change or that rate of moisture equilibration for those materials. Those layers of enclosure, that's what we're really talking about. We recognize that each layer certainly has permeability, but the more layers that we throw up in front of our materials, in front of our collection material, yeah, the slower that object is going to feel it. And we have a number of different opportunities. We're dealing with whatever the outdoor climate gives us, but we've also got the building envelope as sort of our first layer of protection. And maybe the storage room is our second layer, and think about this in terms of what an HVAC system or a mechanical system might do to condition the storage room. But then we have the storage furniture itself. Are we sitting on an open shelf, or are we sitting inside of this gasketed, sealed cabinet? And then inside of that, are we within another enclosure again? Are we looking at a paper envelope? Are we looking at a 4-flap enclosure for a book? Are we looking at, I don't know, some sort of enclosure for a photograph or something else we might be dealing with? But oftentimes another layer, yet again, of buffering. Finally, here's the object. So by the time we put up each of these blocks in front of that object, what is the actual rate that the collection object or the material will feel those extremes of relative humidity? So to sum up and go back through, what we found really is that the enclosures have very little impact on the ability to slow down heat transfer and the ability to slow down the rate of temperature equilibration. But that said, the better the enclosure, the more airtight the enclosure, or even furniture if we're thinking in terms of cabinetry, that those can certainly act as moisture barriers against that external environment and really do give us the opportunity to create these microenvironments that not only smooth out, if you will, conditions for collections, but if we're careful and think about it, we can really avoid some of those extremes or at least reduce the amount of time that is spent at those extremes by using these well-buffered material or by using these well-buffered and materials that are able to act as that moisture barrier to the object itself. Not only that, they also open up this opportunity to think about energy and sustainability and better operation of buildings or mechanical systems without impacting the collections material. You know, as we think about just what our normal arrangements are, our normal shelving or housing situations, just the sheer, how do I want to put this? You know, the very simple formation of what we do in terms of normal housing. Whether it's books on a shelf, or think about the fact that instead of a single sheet of paper inside of a archival records box, now you have a little bit more than a total cubic foot of a block of paper, where sure, there's still some surface area that is going to be exposed to that microenvironment inside the box, but the core of that material is acting now as one object. It is going to take quite a long time for it to fully equilibrate to any environmental conditions to the exterior. This is the, all right, outside of a dog, a book is a man's best friend, and inside of a dog it's too dark to read slide. But if we look at outside the book and inside the book, what do we really see? Well, the RH of the ambient condition, it's all over the place, right? Bumps up and down. The book responds much more slowly, right? It's really not only smooths out those spikes, but notice that here we are in the height of July and August, and we never do reach the full RH condition that is being felt in the ambient environment. The rate to which the book finally equilibrates, or the total RH to which it equilibrates, is a good 5% lower than what the ambient condition is feeling. So how is it that we use that to our advantage? What can we do to try and make that, you know, operate better, not only in terms of preservation for the overall collection, but what can we do in terms of thinking about sustainability and preservation for the long term. Here we are inside of a document case. This is a stack of papers. So think of this as our archival holdings, or think of it as a stack of, no, it's not photographs in this case, but archival collections within a normal metal-edged document box. Again, we've got a lot of fluctuation all over the place in the ambient condition, but when we start to look at the rate of change and at the rate of equilibration for the core of those materials, not only is it much slower, but again, we don't reach the full equilibration of the external condition. We never get to that total RH that's in the exterior environment. We see 49 to 50% RH as our max, whereas the ambient environment outside is getting as high as 58 and even 59%. So again, how can we use this to our advantage and think better about our enclosures and better about our cases to try and slow down this rate of equilibration? And if we think about this on a seasonal basis, here we are, and this is really where some of the strategies come into play. Can we try and find a way to not only just take advantage of this seasonal shift and the buffering that occurs, but is there a way that instead of getting up here to 50%, or more importantly, getting down here to 22%, can we somehow think about making this through operation of the HVAC system, not even with humidification, but just operation and thinking about how it is that we're controlling conditions? Is there a way that we can get to this condition at, say, can we stop the equilibration at 28% or at 30% instead of allowing it to go all the way to 22%? And that's the focus of the most recent bit of research that we're working on between 2014 and 2016, which is, we've kind of defined this project or titled it as a new path to sustainable RH control. And what we're doing here is taking what we've learned from this previous study and saying, all right, we understand what the rates of equilibration are roughly going to be for these different types of materials and these different housing solutions. But is there a way that we can think about mechanical system operation, and can we test different control strategies? In other words, how often a system operates, or what RH set point it operates to at various times of the year if we have that control, to try and measure what the impact on changing or manipulating those equilibration rates may be for the purpose of energy implications. So if we can control that macro relative humidity, in other words, maybe we're using a stepped approach and managing it from, instead of just allowing it to adjust normally from summertime highs to wintertime low RH conditions, can we make sure that it goes from 60% to 50% and allow it to fully plateau and equilibrate to 50% before we allow the ambient environment to drop to 40%, and then allow the material to come into equilibration again? Are there ways or different tests or different scenarios that we can look at that will slow this overall equilibration rate and try to keep and try to avoid hitting those total low relative humidity conditions in wintertime, which are key, as well as the high RH conditions in summer? But can we use the mechanical system to slow that rate of equilibration and never reach those seasonal extremes that existed otherwise? So, concepts to take away from today. I realize we're hitting awfully close to the end. I will try to get to a couple of questions. But concepts to take away: overall, temperature equilibration of most of the library and archival materials that we work with is relatively fast, and this does carry over to museum objects as well. That's something that we can just take by and large across the board. The temperature equilibration is going to be very rapid when we change those conditions on purpose. Now, RH equilibration at the core of the materials that we're working with, again, library and archives media, is comparatively and relatively slow. All things being equal, we're looking at a matter of weeks and sometimes months for full equilibration. So when we think about those short-term fluctuations in relative humidity, from a perspective of chemical decay, the reality that we're dealing with is that the object doesn't feel very much at all. There's still some research and some thought to be given to what's happening on the surface of the object in terms of mechanical change and mechanical decay, but that's what we're moving forward with, and that's what we're working on currently. Enclosures don't have much to do at all with the rate of temperature equilibration. The temp is going to change regardless of what type of enclosure we put it within. That even goes for most of the sealed cabinetry that we're working with. It doesn't do a lot in terms of temperature buffering. It can have a small impact. But beyond that, when it comes to relative humidity and looking at moisture equilibration, enclosures have a lot of potential, and specifically the creation of microenvironments with different enclosures have a lot of potential for being able to not only slow that equilibration rate, but also change the minimum and maximum relative humidity conditions that an object totally feels over time. So I think that's another area where there's more research to be done and sort of more inquiry to be had about what those best models are and what different types of enclosures and what different types of housing structures may give us, and something still to think about in the future. For next time, we're going to go in and talk about building envelopes and a little bit of moisture control and thinking about what it is the building can do in terms of buffering and vapor barriers, simple moisture control, sort of in a passive approach around a building, air circulation, thinking about microclimate problems within a structure, using dew point to identify and think about where ground moisture may be occurring and methods or approaches to try and mitigate some of that. And finally, the consequences of seasonal building closure. So what I want to encourage here for this next webinar in particular is that a lot of this is going to focus on older, maybe historic structures. It's going to really have a lot to do with oftentimes smaller institutions or more historic preservation. So it's something to think about and consider. I hope you can join us for July 8th when we come back and do this again. Project website, as always, if you need anything. This presentation should be up. Give us about 24 hours to get that online probably, and it will be available via that website. As always, please remember to take the survey. It will be emailed out to you shortly. And let's take a couple of minutes and go through and see if we can take a couple of questions real quick. Let's see here. Bear with me for one moment. All right. First question came in from Lisa Rowan. Thanks, Lisa. Do wood cabinets provide much protection as an enclosure layer? It's a really good question, and I have to admit that it's not an enclosure solution that we studied as part of this. By and large, because in general wood cabinets are not accepted as an appropriate manner of housing for a lot of materials. There are off-gassing and degradation concerns with wood cabinets in general. Now, if we had to take a stab at it, and I'm going to say that this is an educated guess, depending on the amount of sealing that is available, they may provide some protection in terms of slowing the rate of RH equilibration or slowing that moisture change. If there are a lot of air gaps, then it's not going to have a lot of impact at all. That air is going to come in through the gap, get into the microenvironment inside of the cabinet, and materials will equilibrate just as rapidly as they would otherwise. But if you're thinking about using wood cabinets as a purposeful buffering technique for enclosures or creating microenvironments, I would just caution you against it in terms of thinking about the impact of the degradation of the cabinet itself, any potential off-gassing and the impact that that might have on the collections that are stored within it. But thanks for the question. And I know there are a lot of people that are sort of faced with that issue, especially when we start looking at museum collections and herbaria and entomological collections. So it's a good thing to keep in mind. Are there any other questions that folks have? Not a whole lot have come in. We're actually totally out. So Lisa, I do thank you for asking that one. But if there are no other questions, I'm just going to say thanks everybody for joining us. I'm glad you can make it today. I hope you were able to take a little bit away from this. I know it's a little bit different than what we've typically been dealing with, but I hope you enjoyed it, and we'll get into buildings and looking more at preservation environments in the next couple of months. So thanks again, and we'll see you in July. Take care.